Okay, this is part 2 of the previous video. What we want to do here, I want to talk about this. We're going to get into continuity. And the way continuity works is if this beam's going to deflect, and again we're kind of speculating on the way it's going to deflect, but let's say the beam did do something kind of like this and then kind of like this or whatever, that the slope right here would be the same at this point here. When x1 and x3 are both equal to L, that the slope here would be the same. So what we're going to do here is we're going to take the equation that we have right here, this one and the one we got down here when we did, let's say this one right here. We're going to set these two equal to one another, because this is the slope of the deflection curves. So we're going to do that now. Scroll down here, and basically what I'm going to say is that when x1 is equal to x3, which is equal to L, then dv1 with respect to x1 is going to equal to dv3 with respect to dx3. Now we go back to that first equation. And we had solved for this one. I'm going to grab this too, and I'll clean it up when I get down here. Let's just grab this part right here. We don't need the dx. Put it down here. Alright, now let's just clean up, and then I'm going to show you where we're going to replace some of this. Take this out, take this out, take this out, and take this out here. Now, earlier we had solved for C1, and we said it was right here. Oh, we'll grab it right here. We said C1 was this value here. Again, this probably seems complicated, but it's really not bad at all. Okay, so we're going to put this value in, take the C1 out, and we put in PL squared over 12. Now again, we're letting x1 and x3 go to L, so we'll take this out of here. Get my eraser. And we're just going to make that into L. Alright. Let's just move this out of the way. I got myself a little bit more space. And I'm going to scroll this over and slide it over to this way. Alright. Now, again, we're going to let that equal to what we had here, which again is just taking this equation right here, grab this, okay, and again we're letting x3 equal to L. It's just I mean, it's tedious. It's not bad. So if I let this equal to L, then that would give me L squared here. And same thing here. Let this be equal to L also. Okay, so now what we want to do is simplify everything we possibly can. So let's see if we can do this on over here. We'll just let's get everything. I'm gonna get everything in terms of 12 right here. So I could write this as minus 3p L squared over 12 plus PL squared over 12. Obviously, on this side here, that would give me a negative 2PL squared over 12. Now we're going to deal with this side over here. I got P over 2 minus 3P over 2. That's going to give me minus 2P over 2, or minus PL squared over 2. That's what I mean, PL squared over 2. and then plus C3 over here. Alright, so far so good. Now move this to the other side. That gives me minus 2 PL over 2 divided by PL squared divided by 12 plus PL squared over 2 is equal to C3. We make this into a 12. We're going to multiply this by 6 over 6. That's going to be a 12 here and a 6 here. P over 2L squared minus 3 has PL squared would just give me minus PL squared, and then that gives me plus C3. Now I'm going to move this to the other side. I'm going to simplify this too as I go. That gives me 1 PL squared over 6 plus, we'll change this to 6 PL squared over 6 is equal to C3. Scroll down. C3 would equal to 5 PL squared over 6. Okay, so now we know that. Let's see if there's anything else here we could solve for. Now that we know, actually we probably can. Let's look and see what we had here. Yeah, we can go back up to this equation. Now that we know C3, let's bring what we had here and we'll solve for another one. And let's see what we knew up here too. Oh yeah, and we knew that was equal to 0, so I should have written that up there earlier. So now we solve for C4. Put that value in, I get minus 7 PL cubed over 12 plus C3. We'll put that value in. We got to multiply by L anyway because we're multiplying by here. So that's going to give me 5 PL cubed over 6 plus C4 is equal to 0. We'll get these into common denominators. It's going to give me minus 7 PL cubed over 12 plus 10 PL cubed over 12 plus C4 is equal to 0. Here we'll get minus 3 PL cubed over 12 plus C4 is equal to 0. So obviously C4, and we'll just simplify that. That's just going to give me sorry, that's a plus. That's going to give me PL cubed over 4. So a lot of work, but we're finally knocking these things out. And now we'll continue on. Okay, and continuing, what you want to note here in this rough view that I have, I'm going to have some maximum deflection between here and here, and the way I would know that would be my slope would equal to 0, and then over here I'd have my maximum deflection, my beam between here and here would have to be at the end. Now since this is equal to 0, what we need to do is we go back to the second equation here, and we're going to set dV equal to 0. Now down below I've already solved for C1, so I've substituted that back in, and we're going to simplify this equation, go all the way down to the bottom. This is my equation here that we had. I substitute back in what I had. Alright, to solve this problem I'm going to get dV is equal to, I'm going to divide it by EI, so I have 1 over EI here. Now what that leaves me inside, I'm going to get the common denominator here. That gives me minus 3p over 12 x1 squared plus PL squared over 12 here. You pull out greatest common, we'll have dV is equal to Let's see, we can pull a P out, and that gives me 12 EI here. What that leaves me inside is going to be minus 3x1 squared plus L over 2. So now if we set dV equal to 0, that's the slope. We'll solve for this. This has to equal to 0. So we have minus 3x1 squared plus L squared is equal to 0. Scroll down. Oops, this is from earlier. I'm going to get rid of this. We're going to solve for this problem right here. Move the L squared over the other side. We'll drop our negatives. That gives me 3x1 squared is equal to L squared. I divide it by 3. X1 squared is equal to L squared over 3. We take the square root, and then x1 is going to equal to L over the square root of 3, or the square root of 3 times L over 3. Either one of those is going to be fine. Now we know where the maximum deflection would occur between, again, between here and here. We go back to our deflection equation. I know this seems really complicated, but we have our deflection equation because we have all our unknowns. We go back to let's see, this equation right here, and we ought to be able to use that one just as stated. And grab that one there. Okay, so now I'm going to rewrite this one in terms of V. Oops, in terms of V. So V1 would equal to divide by the EI. Again, I'm going to pull a P out, and I'll pull a 12 out. When I do that, it gives me negative x1 cubed plus, let's see what we got here, L squared over 12 times x1 . Okay, now I have an x1 in both these, so I'll pull that out as V1 is equal to P times x1 over 12 times EI, and that gives me minus x1 squared plus L squared over 12. Okay, but now we know what x1 is. We know where maximum deflection occurs. It's going to be right here. So now we can start putting everything back in to this problem, and I'm going to use this value right here and put it back in. Scroll down, give myself a little bit more space. Again, this is a very tedious thing, and it's very, very easy to make a mistake. That gives me L over the square root of 3 over 12 times EI. Substitute back into here. If I square those, that's going to give me L squared over 3 plus L squared over 12. If you simplify all that with your calculator, you're going to get some value about 0.0321 PL cubed over EI. Alright, so that's what the maximum deflection would be between the first two supports. Okay, to find the deflection between the second support and the beam, you would have to go back to this equation right here, and we're going to solve for this. Now I'm going to do this down below. Now I'm going to recommend that while you're doing this problem, that you get yourself really organized, especially if there's a test going on, and you start defining these equations as you go. It's too complicated to try to go back and try to find out where everything is located. Now I'm going to go back to V3. I'm going to rewrite this, and you can prove this mathematically if you want to go back through it, but all it's going to be is going to be this value right here. Again, and all we're doing is put in all our C values that we defined earlier, and this should give you the equation. And again, I pulled a 12 out, so they're going to look a little bit different because I pulled out a common denominator. Now, what would happen would be the maximum deflection is going to occur all the way over to here when I get here. Now, this is L, and this is L over 2. So the distance from here to here is going to be 3 halves L. So x3 is going to equal to 3 halves L. Okay, so now if you substitute that in for x3, what you'll end up getting is a value of, let's clarify this. Again, if this is a test, you're going to have to work very fast because this problem eats up enormous amounts of time. So there's your two equations here. That would be your V3. Let me define that too, V3. And again, this is your V1 here. Since this value here is going to be greater than this value here, this is where your maximum deflection is going to be. And again, that is going down because it's negative, and this is deflection is going up because it's positive. Good problem, pretty complicated. Again, the main thing is knowing how to do it and know how to do it fast.